Hey, what's up, guys? This is Chung here. So today, let's take a look at LeetCode problem number 632, smallest range covering elements from K list. So you have K list of sorted integers, right? And then you need to find the smallest range that includes at least one number from each of the K lists. And what is definition of the smallest range, right? Of course, first, if it's 20, we have a 20 and the 25, right? Obviously, this one will be smaller than the 20 and then 26 because the distance in between is smaller, right? Also, if the range is the same, then this 25 is also smaller than the 21, 26. So that's the definition of a smaller range. And then we just need to find the smallest, okay, range that can cover at least one number, right? And then we have some examples here, right? So the first one is this one. The answer is 20 to 24, and then we have some other examples, right? And here are some constraints. So k to this one is going to be 3,500. So maybe you can do a up to n square time complexity for that. But that's actually the length of the list, and then for each list we have up to 50 numbers here. So I think the first one is a good example here, right? Basically, we can just use this one as an example here. Try to see how we can solve this problem. So we have this 10, 15, 24, 26. So we have 0, 9, 12, 20, and then we have 5, 18, 20, and 30. Okay, so that's the three lists we have here, right? So so approach for us is that we want to basically we want those three numbers from each list as close as possible, right? So obviously, we'll try to start from this beginning here. We're gonna try to start from this is gonna be our initial state, because if we to select the smallest number from each of the array from each of the lists here, we have starting point basically. That's going to be our starting point, which will be going to be 0, 4, and 5. So for this one, we have the range is 0 to 5, right? So now, as with this one as a starting point, so how can we explore? Can we explore the rest of the numbers and to find the range, right? So common approach is that we're going to increase the lower bound for this range, which is 0. So the reason, and we basically there are two approaches, right? So we can either increase the lower bound, or we can decrease the upper bound. Okay, but since we're traversing, traversing from the left, which means, and also because each list is sorted from smallest to biggest. Basically, there's no way we can bring the biggest number down, right? We can only try to increase the lower bound up, so that we can try to find a smaller range, right? So from 0, and the next one is 9, right? So we have 9, 4, and 5. So we have range of what, 4 to 9, right? And similarly, so the next smallest number is 4, right? 4, the next one is 10. Basically, we have 9, 10, and 5, right? And then we have 5, 9, 10, 18, right? And then the next one is 9, 12, 10, and 18. So basically, we just try to always bump the lower bound each time to try to find a smaller range. So this one is similar like a greedy approach, right? Every time we're trying to bump the lower bound so that we can have a better chance, right, to find a smaller range along the way. And since we'll always maintain the smallest and the biggest numbers of the current range of the current sliding window, so it's gonna be like a k size of the window we're trying to maintain here. So it's guaranteeing that the current range will always cover at least one number from each of the lists here, because we're getting the smallest to the biggest, right? Of course, this range can cover at least one number for each of the from each of the k lists here. And when do we stop, right? So for example, if we have like we have a list from this one 24, 22, and 20. So when we reach this state, the current smallest number is 20, but 20 is the end of this list here, right? So there's no bigger number uh, for 20 in this list, and that's when we need to stop, because the because it means that there's no way we can keep increasing the lower bound anymore, right? Since we have to at least include at least one number for each of the case lists, which it means that we cannot change this 20. But the rest numbers, if we change the rest numbers, we can only change them to a bigger number, not a smaller one, right? Because we're always like trying to loop through to the right side, which means that there's no way we can find a smaller range anymore. That's when we need to stop. Okay, so that's that. And yeah, now back to the range here, right? Since we need to maintain the current smallest number, right, and the current maximum numbers, right? So basically, we need to maintain the minimum and the maximum. Okay. So at the beginning, since I saw this one, okay, so we just need to know the current minimum and the current maximum numbers. I was thinking that I was going to use like a monotonic queue to maintain these two values, because with a monotonic queue, we can get the minimum and the maximum numbers within the sliding window in O1 time, right? Uh, but there is an issue for this problem. But the reason we cannot use the monotonic queue here is because after getting the minimum values, for example, the 0 here, the next one could be the second smallest number, which is 4, right? If we use the monotonic queue, right, it means that we could we could this 4 could be over could get overridden by this 0 here, right? So which means because of the characteristics of a monotonic queue, it only guarantees that you can get uh, the smallest number of the current sliding current sliding window. It does not guarantee that you can get the second smallest number. That's why we cannot use a monotonic queue, right, to maintain that. Basically we want to maintain like a complete list, right? So that we should use a priority queue or a heap, because the heap or the priority queue can give us the smallest number, right, within a log n time or log k time, right? Assuming we have a size k list, right? So that's why we choose the priority queue to maintain the current minimum numbers. And then every time when we pop these minimum numbers out, right? Since we also need to find the next number of the current numbers, which is 9 in this case. So in the priority queue, besides the number itself, we also need to store some other data related to this number, which is the list index. Uh, what's the index for this list, right? So it's gonna be I'm using a list index here, right? And then the next one is the number index. Okay, the number index. so which indicates that which position the current number is, so that we can use it to check if we need to stop the current loop, the whole loop, or and how can we find the next number. So that's how we maintain the minimum values, right? And then for the max values, okay, so for the max values, it's we can just simply use like a global max variables, to maintain that. Basically, every time when we see a new number, when we find a new numbers, we always compare if it's greater than the current max number. If it is, then we update that. If it's not, we simply do nothing. Okay, and why this? I think this should be pretty straightforward, right? So this max number works because when we pop the smallest number from the priority queue, since it's the smallest number, it will not affect the current max number. Okay, which means that the max number is still in the remaining numbers, right? So that's why, after popping the current numbers, and then we find the next number of this list here, we can simply use this 9 to compare with the current max number, because the current max number are still in this range here, because the priority queue pop will not affect the max results. Okay, and the only exception is that if there's only one list in total. For example, if we only have this one list, and then every time when we pop the priority queue will become to empty, right? And then the next one is, for example, if the first one is 4 and the next one is 10, right? So when we have 10 here, the basically the minimum and maximum, they will both become to 10, because the maximum was 4 before, right? And then the next one is 10. So when we compare 10 with 4, then we always get we'll always have the current number as the current maximum number. So that basically our approach or our algorithm should work. Yeah. So I think that's it, right? I mean, with that being said, I guess we can start coding. I mean, the code is it's not that long, so it should be pretty easy to understand. So first one, the priority queue, and then we have a length of the nums, right? And then I'm going to design like a global, like a max variables. So the first one is we populate initial state, right? Which we need to add the first element of each list to this priority queue in range n here, and then heap queue dot heap push, right? So this one priority queue. So like I said, besides the number itself, so we're always pushing the zeros, right? We also need to maintain the current list index, which is I, and the numbers index, which will be 0 in this case. Okay, and we also gonna be maintaining this max, right, with the nums I dot 0. Okay, and then we can just initiate our final answer. Sorry, the initial answers, not the final answer. So the minimum value is the priority queue, the first one, right, of the priority queue of the 0, which is the value itself, and then the upper bound is the maximum, current maximum. And the next one is we do a while loop, right? So we try to explore all the possible, the better range, right, by having the next numbers. So we have current numbers, but I think actually we don't need current numbers here. So we have a list of index. We pop these things out, right? Gonna be the current minimum numbers. We have a number index. Do a heap q dot heap pop priority queue dot yeah, that's priority queue. And then if the num, right, of index is equal to the length of nums dot list index -1. Then we just simply break. So what I'm doing here is that if the current smallest number is the last element, last item, right, in its list, then break, because there's no need, because we cannot find a smaller range anymore. Okay. Otherwise, right, next number going to be the numbers dot list index and then the num index +1, since we're looking for the next number, right? And then we update the max. Basically, every time we have a new numbers, we update the max. Next number. And then we update the heap, right? Maintain the heap push the priority queue, and similarly as now it's the next number, right? And then the I is the same still, because we're still using the same list index, but for the num index, it should be num index +1. Okay. So now let's just to update the final answer, right? If the max minus priority queue dot zero, right, smaller than the answer dot 1 minus answer dot 0. Basically, if the range is greater, it's smaller, we update the answer with the new lower and upper bound, right? So priority queue dot 0, 0, and then the upper bound is, of course, is the max, right? And then in the end, we simply return the answer. Yeah, so that's it, right? I mean, so this one will also handle the second scenarios here, where if the current range and the previous range are the same, we're only maintaining the previous one, the range with a smaller starting point, because we're always looping through each of the lists from smallest to biggest. So which means that if for the current one, the current range, it's always have like a bigger start comparing with the previously range, right? In case the range value is the same. That's why, since this is strict smaller, and the answer, in case of a tie, right, of the range, we're only maintaining the first value, the first range, which is the smallest starting point. Cool. I think that's it, right? So if I run the code, accept it. Yeah, so it works. I mean, yeah, so and for the time and space complexity, right? So assuming the total numbers equals to n. So total numbers, n means that, for all the k list, we have n numbers, right? And then we have a total list, right? Equals to k. So like I said, to maintain the priority queue, do a heap pop and heap push, we need a log k time, right? And so for the worst case scenario, each number needs to be pushed and popped into and from the priority queue, which means that we have n times log k. So that basically this is a time complexity. And space complexity is obviously O of k, because we're maintaining like size k of the priority queue. Yep. And that's that. So, and there's like another approach, a solution for this problem. Basically, we just do a global sortings for all the numbers in all the case list, and we also, so after the global sortings, and we need to we're scanning we're going to have like a left and the right pointers. We're going to use the 2 pointers to maintain like a sliding window that have basically have at least one numbers for each of the k list. So to do that, we also need to maintain the similarly, besides the number itself, we also need to maintain the index informations for that, so that we know how many lists we have included into the current sliding window, right? We only update our values, right? Whenever the current sliding window uh, includes a case list. Okay, so I'm not going to implement that, but to be able to do that, we also need to use like some counters, right? The counters, right? The counters for case list. Basically, if every time when we move the cursors, right? When we have like a new right pointers, we increase the counters for this list that this R represents. When we shrink the left pointers, we decrease the counters. And whenever the counters for list equals to 0, we delete the counters, right, from the dictionary. And that's when we yeah, and that's when we need basically that's when the length of the counters will be decreased by 1, right? And we will only update the final answers when the length of counter is equal to k. And yeah, and when we have like sliding window, obviously, the minimum value is the left pointer, and the maximum value is going to be the max point. It's going to be the right pointer, right? And that's how we maintain that, calculate these informations. But the time complexity for this approach, it's going to be since we're going to do a global sortings, so it's going to be unlog log n, right? And obviously this one is slower. It's greater than the n log k because n is greater than k, right? That's why the second solution, this solution is better than this one. Um, yeah, I think that's everything I want to talk about for this problem. Yeah, hope you guys like it. And yeah, I'll stop here. Thank you for watching this video, guys. Stay tuned. See you guys soon. Bye bye.